Welcome to Fundamental Chemical Laws. So, Antoine Lavoisier measures the mass of reactants and products of various reactions, and he was able to find that the law of conservation of mass holds. So, mass is neither created nor destroyed in a chemical reaction. If I start out with 10 grams of reactants before a reaction, I must have 10 grams of products after the reaction, or 10 grams of a mixture of reactants and products. So he was able to find that combustion involved oxygen, not this phlogiston stuff that I mentioned in the last video. And oxygen is also essential for life. So if I put you in a box without any oxygen, or I put you in a box and wait a while, you'll use up the oxygen, just like a fire will use up the oxygen, and you will go out just as the fire goes out, right? You will die if you don't have oxygen. So Joseph Proust comes along and he finds the law of definite proportion. So he discovers that copper carbonate is always 5.3 parts of copper to 4 parts of oxygen to 1 part of carbon. So by mass. So if he measured 5.3 grams of copper and 4 grams of oxygen and 1 gram of carbon, that made copper carbonate. If he added any extra, say, copper, well, it wouldn't react. You'd still have some copper left over. You wouldn't then get out of that more copper carbonate. So what he was actually doing was he was taking a sample of copper carbonate and breaking it down into copper and oxygen and carbon, and this is the ratio that he found. Now he said, well, if I'm always getting this same ratio, and he then looked at some other compounds as well, he said, if I'm always getting the same ratio, then there must be some law of definite proportion. That a given compound always contains exactly the same proportion, a definite proportion, of elements by mass. So now, note here that he's not saying anything about atoms. Right? All he's saying here is the masses involved have to be a set ratio. But he doesn't have a good way of explaining why that is. So then along comes another chemist named John Dalton, and he reasons that, well, if elements were composed of tiny individual particles called atoms, and he's basically borrowing the Greek word atomos, then a given compound should always contain the same combination of these atoms. So if our copper carbonate always contains a set number of copper atoms and oxygen atoms and carbon atoms, then it's always going to have the same ratio by mass. So, this is where his law of multiple proportions gets introduced. Dalton noted that carbon and oxygen form 2 different compounds, and those compounds contain different relative amounts of carbon and oxygen. So at first glance, this appears to violate the law of definite proportion. But he found, no, that's not true, because there are 2 different compounds. Compound 1 has 1.33 grams of oxygen that combine with 1 gram of carbon. And compound 2 has 2.66 grams of oxygen that combine with 1 gram of carbon. So, what this means is that one of the compounds, compound 2, has double the oxygen that the first compound has per amount of carbon, whatever you. Now, we of course know that it's atoms, but he didn't know that at the time. So, if this is true, these results are easy to explain if atoms exist. Because we can say, well, compound 1 is CO, carbon monoxide, and compound 2 is CO2, carbon dioxide. That's easy to explain, but only if atoms exist. If atoms don't exist, if we could mix some fractional amount of oxygen with a carbon, well then this shouldn't be. We should be able to get any infinite number of compounds between carbon and oxygen. We should be able to get, you know, a ratio of 1.0 grams of oxygen and 1.0 grams of carbon, or 1.5 or 25. But the fact that we don't means that there has to be something at a very small scale that we can't see that is limiting how these 2 elements are combining. And the only way that Dalton was able to do that was by saying that atoms existed. So, his statement of multiple proportions says when two elements form a series of compounds, as carbon monoxide and carbon dioxide do, the ratios of the masses of the second element to that combine with the first element, with 1 gram of the first element, can always be reduced to small whole numbers. So, if we look back at this case, this ratio is just double the top ratio. 2.66 is double 1.33. And so we must have twice as much oxygen here as we do up there. And he noticed that for any different series of compounds that he could look at, that this was always true. He could always divide them and get a small whole number ratio. He never had something that said, well, this one should be 1, and that one should be 1.5, and another one should be 2. He never found that. Now, of course, if you have 1 and 1.5 and 2, well, you could just double them all and say, well, it's 2 and 3 and 4. And so this is what he was able to do. He was able to look through the various compounds that were composed of the same elements and see there always is this small whole number ratio, and that's what he names then the law of multiple proportions. You may have multiple proportions, unlike the law of definite proportions. It says there's only one ratio. He's saying, well, there may be more than one ratio, but those ratios can always be reduced to small whole numbers. And so now we have some evidence for the existence of atoms, right? Democritus proposed the existence of atoms, but he never was able to prove, or he never really had any evidence for it. And so the idea of the existence of an atom sort of sits around for 2,000 years. But now that we know that atoms exist, we finally have some proof for atoms. Now chemistry can really get going. Now we can really start to look at, well, what is the structure of atoms? What are these atoms made of? Do we have different types of atoms? Well, we know that we have different types of atoms because we have different elements. But how many different elements do we have, right? So now chemistry, the study of chemistry, can really, really start to get moving. So this is fundamental chemical laws.